All right, let's get started, shall we?
Yes.
Yes, we shall, as I talk gloriously. Yes.
Start asking questions?
Start asking questions, that's right, yes. All right, go for it, yes.
Could you explain like the difference between a tropical year and a sidereal year?
Yes, sidereal year versus tropical year. Yeah, I'll do it very quickly because that's actually something I plan to do in class, and it's in chapter S1, which we didn't read. So there won't be any questions on the exam, but a sidereal year is the time to go from the March equinox back to the March equinox again. Sorry, the tropical year is the time to go from the March equinox to the March equinox. The sidereal year is how long it actually takes the Earth to go around the Sun, 360 degrees. And because of precession of equinoxes, they're different because the Earth won't be exactly in the same place in its orbit by the time of the next March equinox. Now, precession of the equinoxes could be on there, but sidereal year versus tropical year is not going to be on there because we didn't cover it in class and we didn't read that chapter. So, sad but true. I know it's disappointing.
I'm okay
You're okay with that?
with that.
Yeah, okay. All right. Well, as long as it makes you happy. Yes?
Can we talk about the sidereal day, and solar day?
Sidereal day versus solar day. Absolutely. Yep. So the idea there is, this is actually, let me pull this up from one of the lecture tutorials. So the figure. So hang on for a moment. Let's see. Sidereal day versus solar day. So, chapter. Sidereal day versus solar day. So that's one of the lecture tutorials we did is about that. And the idea here is it's because Earth is going around the Sun that there's a difference. So the sidereal day is how long it takes the Earth to actually spin by 360 degrees on its axis. And so if you think about it, suppose some star was on your meridian. So on the north-south circle that passes over your head, at its highest point in the sky, maybe we're facing south to see it, although if its declination was north enough, you might be facing north to see it at its high point. But in any case, it's on the meridian. So when Earth spins through 360 degrees, that star will be back on the meridian again. On the other hand, Earth is orbiting the Sun, which means consider when the Sun is on the meridian. A solar day is the time for the Sun to be on your meridian and get back to your meridian again. That's different because of the fact that we are orbiting the Sun at the same time that we're spinning on our axis. So to use, that's a little bit more than I wanted, to use this figure to illustrate here from your book, the idea is, imagine that the Sun just happened to be in front of some distant star one day, and the person here represents the Earth going around the Sun. So suppose the Sun is in front of some distant star seen from Earth, then the Sun and that star would come to our meridian together. Now, if Earth wasn't going around the Sun, when it spun around 360 degrees, the Sun would still be in front of that star, and so the Sun and the star would get back to the meridian at the same time. However, we're going around the Sun. So the next day, will the Sun still be exactly in front of that star? No, because we've moved in our orbit, so our line of sight no longer has it going from pointing to the Sun to that star. The Sun will have moved a little bit along the ecliptic because of the fact that we're going around the Sun. So that means that when you've spun 360 degrees, the Earth's so-called the amount of time for the sidereal day, then you'll have the star get back to your meridian again, but you'll need to turn some extra in order to get the Sun back on your meridian. So, for example, if I am pointing at the sun right now, and I am the Earth, okay? This is the sun, apparently, yes. So now, I spin around 360 degrees, so my arm is parallel to where it was before. So if I was pointing to some really distant mountain, I'd still be pointing in that really distant mountain. You guys are close to me, so as a result, it's a little deceptive. But in other words, if I was pointing at a star before, I'd still be pointing at that star now, because the star is many light years away. But am I pointing to the sun anymore? No. So to point to the sun, again, I got to keep turning some in order to point to the sun. And in fact, you have to turn about 1 extra degree, because Earth goes around the sun about 1 degree every day, since there's 360 degrees around the orbit, and 1 day is roughly 1/360th of the orbit, really 1 over 365.24, blah, 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 but whatever. The Earth goes about 1 degree around the sun every day, which means, by this figure right here, it has to spin about 1 extra degree, which takes about 4 minutes. So the solar day is about 4 minutes longer than the sidereal day. Another way to understand it would be in terms of the celestial sphere. If I were to put the sun at some point along the ecliptic here, and then I have the sun on the meridian someday, now I spin the globe around, is the sun at the same place the next day? No, it's moved on the ecliptic. Not much. It's the width of these little, I know you can't see them back there, but there are those little green and black bars along the ecliptic that are each 1 day's worth of motion. The sun has moved a tiny little amount, so that by the time the same right ascension is back on the meridian again, the sun has crawled a little bit away, and so the celestial sphere has to turn a little extra to get the sun back on the meridian again. Of course, what's really happening is Earth is turning around, but what it looks like to us is the sky has to turn a little bit extra to get the sun back on the meridian again, because the sun has been crawling slowly along the ecliptic. Think of it as like there's a little ant crawling along the ecliptic there, and as a result, you have to keep turning the globe a little extra to get the ant back on the meridian again, because it's crawling the opposite direction along the ecliptic. That's why there's a difference.
And we keep time basically with it.
No, we keep time by the mean solar day, and that's because we want time to be based on where the sun is in the sky. If we kept time by the sidereal day, then what would happen is, sometimes of the year, 12 p.m. would correspond to it being dark outside as a result. Because suppose it's 12 p.m. with the sun high in the sky today. The sun's been moving along the ecliptic, so 6 months later, when that same position on the sky is back on the meridian again, the has moved halfway around the ecliptic, and so it would be night when it was 12 p.m. on our clocks. We don't want that, so we keep time by the sun, is what it comes down to. So we keep time by what's called the mean solar day. Our clocks are based on the mean solar day, which is the average amount of time it takes the sun to go from the meridian back to the meridian again. That varies a little bit over the course of the year, so we use the average amount of time it takes the sun to appear to go once around us, back from the meridian back to the meridian again. Any other questions about that? I always like to give a chance for follow-up before we move on to something else. All right, what's next? Yes?
Okay, so when you're talking about the precision of the equinoxes,
The precession of the equinoxes, yes.
It says no its implication with regard to the pole star, like the Polaris. Can you kind of explain like the implication of that?
Yeah, what is the implication with regards to Polaris? So here is a globe that can be used to illustrate the idea of precession of the equinoxes. So this globe, even though it's not obvious to casual inspection, is a special globe because the bottom's been cut out of it, and there's a big iron yoke in here trust me, I can build my muscles by doing this. This thing is very heavy. And I suspend it on this little point on here, and that big iron yoke puts the center of gravity underneath the pivot point so that if I tip this thing, it wants to rock back and forth like that. So this allows this thing to behave literally like a top, like when you were a kid, right? You spin a top and you notice it goes. That's the idea with precession in a lot of ways. So this thing is going to precess because of Earth's pulling down on its center of mass gravitationally. The actual Earth precesses for a related reason. So the idea is Earth is spinning, and that sort of flings the equatorial regions outwards. So Earth, it's a small effect, it's greatly exaggerated here, but the Earth's equatorial diameter is actually a bit bigger than its polar diameter because of the fact that Earth is spinning. And that means Earth has a so-called equatorial bulge, and the gravity of the sun and the moon pull on our equatorial bulge. And if you look at the picture here, like where this would be like for a full moon, notice that the moon is trying to pull the bulge piece closer to it upwards, and the sun is trying to pull the bulge closer to it downwards. The sun and the moon together are, in a sense, trying to stand the Earth upright, trying to undo that 23.5-degree tip that it has. Now, if the Earth weren't spinning, the effect of that would be to actually cause the Earth to rock back and forth, and there would be some damping, and it would actually end up standing it up after a while. Just like with this globe, if I don't spin it, then what happens pretty quickly if I tip it over is it has what we call a damped oscillation. It rocks back and forth and eventually stands straight up again. But if I'm spinning it, it behaves like a top, or the fancy word is it behaves like a gyroscope. And what that means is, and it's actually fairly complicated to do all the torque and stuff like that, like in a physics class or whatever, but what it means is that instead of rocking back and forth, it does what we call precessing, like a top, where the direction that the axis is pointing changes with time. See how it's wobbling around like that? That's precession. So the Earth is undergoing precession, and that's supposed to be indicated on this figure here. So I'm going to keep changing the lighting situation here. Earth's axis of rotation precesses around, but it's a lot slower than that top. It takes about 26,000 years for the direction of Earth's axis of rotation to go once around due to precession. And here's another picture of that idea. So here is the Earth spinning, and today Earth's axis of rotation is pointed very nearly at Polaris, what we call the North Star. But it isn't always so because of precession. The direction in space towards which our axis of rotation is pointing changes with time because of this wobble. And so, for example, in the year about 15,000, the axis of rotation of Earth will be pointing closer to the star Vega, not as close as it is to Polaris today, but it'll be pointing more towards Vega and not at all pointing close towards Polaris. So in other words, where the North Celestial Pole is on the sky changes over time. Now it's close to Polaris, but notice in the year AD 1, it wasn't nearly as close to Polaris as it is now. Polaris wasn't that great a pole star back then. Even in the time of Columbus, Polaris was quite a bit further away from the North Celestial Pole than it is now. It wasn't as useful a pole star. The pole will get closest to Polaris in about the year 2100, and it'll start to pull away from it again. In the time of the ancient Egyptians, a star called Thuban in the constellation Draco was the pole star. And so precession causes where the North Celestial Pole and South Celestial Poles are to change over time. And so as a result, Polaris just happens to be a good North Pole star today, but it wasn't always so. And It will be again in another, 26,000 years, but right now it's close to as good as it can get as far as being a pole star is concerned. And then the implication beyond that is that if where the poles are is changing, so is where the celestial equator is. So is where the celestial equator intersects the ecliptic. So in other words, where the equinoxes are along the ecliptic and where the solstices are along the ecliptic is changing with time due to precession of the equinoxes. That's why it's called precession of equinoxes. So you guys remember, what is the name of the constellation that the sun is in these days at the time of the June solstice? Do you remember back from when you did the celestial globe worksheets? Starts with a G, Gemini. It's in Gemini. Now, that means its declination will be 23.5 degrees, and the circle on Earth, which has that declination, which has the sun overhead on the June solstice, what do we call that? That's the Tropic of, is it the Tropic of Gemini? No, it's the Tropic of, that's the south one. The Tropic of Capricorn is the southern one. The Tropic of Cancer is the northern one. Back when those tropics were named, precession of the equinoxes meant that the solstice was actually in Cancer back then. The June solstice was in Cancer, and the December solstice was in Capricornus. Now the June solstice is in Gemini, and the December solstice is in Sagittarius. So those tropics have the names corresponding to where the sun was at the solstices back in ancient times, not these days. And in fact, for similar reasons, most people, the sun is in the wrong constellation, so to speak, astrologically speaking, when they were born. For most, the precession since the ancient times when the sun signs, quote unquote, were created happened, has caused where the sun is along the ecliptic to be about one constellation over for most people from their so-called sun sign. Which is one more reason why astrology is bullshit, basically. I mean, your sun sign is just, it's not where the sun actually is for most people. Yes?
Maybe, I don't know, but so when it says like be familiar with the phases of the moon,
Yeah.
positive, is that what we did in extra credit kind of?
It's the extra credit, it's also the exercises on the phases of the moon. In other words, that thing that I said that I wouldn't be collecting, but that, yeah, you're holding up one right there, right, that I handed out to everyone, that thing right there. So definitely work through those things, because on there, I promised that there would be questions based on that, just like those, except change the details on the exam. I kept my promise. There are exercises from that based on that, just with, the phase or the time of day or whatever changed. There are questions like that on the exam. And so you do want to do those and be sure you understand how to do those. And then also you want to be able to, if you see a picture of the moon, you should be able to say, oh, that's a waning gibbous. Oh, that's a waxing crescent. You should know where the Earth, where the moon would be in its orbit relative to the sun. If it's waxing crescent, where is it relative to the sun in the sky, in its orbit, that sort of thing. You should know all that too. Yes?
How many multiple choice are there compared to short answer?
There's, I think it's, if I'm recalling correctly, it's like 36 multiple choice, and then there's like, I think it's 7 or 8 short answers, but the short answers can be, like a page, and short answer can be like, fill in a blank and then write a sentence or two to explain it, that type of thing.
Okay.
So, yeah. Yes?
Talk about like the phase of the moon, when we actually look at them, I can actually understand them when I look at the pictures.
Uh-huh.
But those things that in masculine astronomy with the circle, and then that really confuses me.
So like when, are you talking about like there's where you got the earth spinning, or somebody standing there and they're supposed to?
Exactly. Like, it's just like pointing out how which part of the moon is the brightest and which is the least brightest. It's like putting all of them together, but then all the phase of the moon confuse me when they're on that diagram.
Maybe I should, let me call up the Mastering Astronomy and you can tell me like what part you're talking about here.
I think it's the last exercise.
Okay. Is it the tutorial that was with
No,
it, or is it
no.
not? Okay, so let me, you may have issues using this website. Oh, okay. I will, oh yeah, I do want to enable pop-ups. Okay, let's see, so, always allow pop-ups from Pearson. Okay, there you go, Pearson. Browse. And,
I mean, I can answer the questions.
yeah. So, here we go, sign in. Oops. Right, and then of course, I'm happy too, if you want to do an example from like the moon phase exercises, I'm happy to talk about anything like that too. Okay, so that's in, that's in the
Sections.
the section 3-4 one, right?
Yeah.
Okay, so here we go. Here's the student view. So which one is it? You know?
And this one.
Which one?
It just goes pretty slow, I'm just trying to find it.
Oh, okay, okay.
So it might be, I think I know what he's talking about, I think it might be lunar phases, 2. the
Lunar
rain
phases
forecast.
2. So let me bring up
Yeah, it is lunar.
lunar phases 2. Okay. Lunar phases 2.
Yeah, that's what I.
Okay, here we go. So this guy right here?
Yeah.
Okay. So let's chat, shall we?
If
All
I
right.
actually look at the one in the book, it's kind of like explaining everything through a picture. So
Mm-hmm.
if I actually understand the picture and
Uh-huh.
actually relate to that visually, I can create the sign.
Okay, so let's talk about that because I'm guessing you're not the only person that's true for. Is this first one to do here? This,
Yes.
yeah, okay, so let me remind myself of what I do all of these myself, but then, it's been a while since I did it. So the following figures show a top view of Earth, sunlight, and 6 different positions of the moon as it orbits Earth. Note that the distances shown are not drawn to scale. Rank each of the 6 lunar positions from left to right based on the amount of the moon's illuminated surface that is visible from Earth from greatest to least. If 2 diagrams have an equal amount, put them on top of each other, right? So we want basically how lit does the moon look to us for all of these, and we want to go from, what did it say it went from, was it greatest? Yeah, from greatest to least. Okay. So here's how I approach that. Let me erase some board here. And let me make it the same direction that the sunlight is coming from. The sun's off on the right there, okay? And so here's the moon's orbit. Here's Earth, sunlight. All right, so what 6 positions do they show? I'm just going to show 8 positions if I feel like it. Okay. Yeah, I'm just going to do these 8 because these are kind of quote unquote standard 8, so to speak. Okay, so here's Earth. Moon. All right. So in all cases, what fraction of the moon's surface is actually lit by the sun in all cases? Half. That never changes, right? If you're standing upside down in a herd of stampeding cattle, how much of the moon's surface is actually lit by the sun? Half, right? What if it's a stampede of bunny rabbits? It's still half, right? It's always half, no matter what. So, it's going to be which half here? The right half, right? Because the sun's often this way, so it's got to be the half facing the sun, okay? So let's look at this one right here, for example. I'm going to shade it in white, the part that's lit, okay? Now, if you think about it, what we see from Earth is half of the moon, the half which is on the side facing us. So if I use this meter stick here, what's always true is, if I draw a line from Earth to the moon, it's if I put this meter stick perpendicular to it, that's the dividing line between the half that's facing Earth and the half that's not facing Earth. So for example, right here, I can draw in this line right here, and there. And it's this side of the line that's facing Earth, okay? So now, let me kind of take in the super zoomed in view. Here's the moon. There's the lit half. And that's the side facing Earth. So, of the side facing Earth, am I seeing mostly lit or mostly unlit? Mostly unlit, right? I'm seeing a little bit of lit and mostly unlit. So what kind of phase is that? Crescent. It's got to be a crescent phase. If you're seeing mostly unlit, it's a crescent phase. If you are seeing mostly lit, it's a gibbous phase. Now, waxing or waning depends on where it is in its orbit. Depends on where it is in its orbit. But like for this one over here, if I do the same kind of deal, for this one over here, super zoomed in view. For this one over here, here's the side that's facing us. Mostly lit or mostly unlit? Mostly lit, so it is gibbous, right. And the waxing part comes from, what phase is this? New. And if we're looking down from above Earth's North Pole, which is how we usually draw it, which way is the moon going? Is it going this way, or is it going this way? Counterclockwise or clockwise, looking down on Earth's North Pole? Counterclockwise, right? Moon is going around this way. So if I go from new, then I'm going on the waxing side until I get to full. So new, what's this? Waxing crescent. This is first quarter. This is waxing gibbous. This is full moon. Waning gibbous. Third quarter. Waning crescent. New again, right? So that's the key to doing this. Each part of it. Yes?
So the moon rises in the west.
I did not hear that. The moon, just like the sun, rises in the east.
No.
East.
But, okay.
No, it doesn't.
No, seriously, it does.
Let's get out of my mouth.
Okay, but let's. Right.
But I remember, like, today for the extra credit though, I thought at least, that the moon was the opposite of
We
what
did, she
the
yelled
sun.
at us. that we
Field
were
was
wrong.
that.
Oh, she did?
Yeah.
So I didn't hear her yell then?
She just looked at me and she was like, that's stupid and wrong. And I was like, "Oh, okay." But in a nice way. Like, basically, it was like, you're just wrong.
Oh, that's stupid and wrong.
Well, I did the whole class and I was like, wow, I know what's happening. And I walked in and she shut me all the way down.
So we got that in our heads now, we were wrong.
Okay, so let's unget that.
Unget that, okay. So it's the same as everything else.
So, right.
It rises
The-
in the east and
right.
sets in the west.
Everything rises in the east and sets in the west unless it's circumpolar, in which case it does neither. It just,
And it
then it just circles around the north celestial pole, always above the horizon.
Okay.
Yeah, no matter what it is, it rises in the east and sets in the west. Now, it might go very far north of east or very far north of west, depending on where it is and where you are. But it rises at least, it rises somewhere on the east between north and south and sets somewhere in the west between north and south. That's always true.
Okay.
Yeah. And that's because,
Change it for this time.
Earth is spinning on its axis from,
West.
yeah, what's it say while it's spinning? What does Earth say while it is spinning? Whee! So it's spinning from west to east, but then the sky goes the other way, from east to west. And
Okay, so the sky that goes,
the sky goes from east to west.
the earth goes from
Oh,
west.
the Earth spins from west to east, but what we see is the sky spinning the other way around. The sky spinning from east to west, which is really just because we're on the Earth and we don't notice that it's actually the thing spinning.
Okay.
Right. Yeah.
And the reason that we
takes to orbit and the time it takes to spin once is the same. So if I'm staring at you, the Earth, as I go around you, right, as I go around you, then if I always stay facing you, then I am spinning on my axis, right? Because back there, when I started, I was facing the back of the room. Now I'm facing you on so now I'm facing your right, the right wall of the room, right? So I went 1/4 of the way around you, and notice I went from facing to the back, I spun 90 degrees to facing the right side of the room. So I spun 1/4 on my axis, and I went 1/4 of my orbit around you.
Okay.
That's why we always see the same face of the moon, because its orbital period and its rotation period are the same as one another. The time it takes to orbit us once and the time it takes to spin once on its own axis are the same. So, yes?
One of the questions that the master in astronomy asked about, from the perspective of the moon, what is the phase of the Earth?
Yep.
Is it just the opposite, so it's
It's the
waxing crescent,
opposite,
it's waning
yes.
gibbous?
Yeah, if we see waning crescent, the moon sees waxing gibbous, for example. It's always opposite, because notice here, back to this picture again, right? Here is the waxing crescent moon, right? If the moon is looking at the Earth, does it see mostly lit or mostly unlit? Sees mostly lit. So it's a gibbous phase instead of a crescent phase. And furthermore, it's waning there because as the moon keeps moving in its orbit, notice it's moving towards making the Earth go to new, to seeing the unlit half of the Earth. So the phase that the moon sees of the Earth is sort of opposite of the phase that we see of the moon. Yep. Yes?
Is everyone at home moving into different? I don't really know how to describe right ascension and declination. Like, how do I?
Uh-huh. Okay, what is right ascension? What is declination? Yes. So, we've got latitude and longitude on the Earth. Right ascension and declination are celestial, essentially, latitude and, are celestial longitude and latitude. So, let me find a figure to illustrate that. It's on the moon phase. I mean on the celestial globe exercises, but it's probably best if I pull up, because I didn't put it on a PowerPoint this time, or a slides presentation this semester, because it's in that exercise, but I have it in prior years. So let me pull it up that way. So hang on. 2015 spring, last time I taught this, which is amazing to me. I thought I taught it more recently. Presentations and chapter 2.
So I'm like waiting until the last minute.
I don't even have a job. I know where let's see.
I was the first class.
All right. So this shows the idea of right ascension and declination. Okay, so declination is like latitude on Earth. It's angle away from the celestial equator as seen from the center of the celestial equator. Just like latitude on Earth is actually angle away from Earth's equator that you would see if you were at the center of Earth, which I don't recommend because it's hot as hell down there, but whatever. So here's the celestial equator. What's its declination? 0, okay? And then we have this convention, because of northern hemisphere bias, I guess, although negative numbers are perfectly good numbers. If the declination is positive, it's northern declination. If it's negative, it's southern declination. So what is the declination of the North Celestial Pole? What is its angle from the celestial equator as seen from the center?
90.
90 degrees, right? Yeah, if I'm pointing at the north celestial pole, the equator is 90 degrees away from it. So the north celestial pole is plus 90. What about, I can't see it here, it's hidden. What about the south celestial pole? Minus 90, okay? And then notice there's 1, 2 circles here, and then a third all the way up to the pole is how far you'd be going. So notice this is in 3 equal divisions here. So this circle right here must have what declination? It's 1/3 of the way up to the pole.
30.
So this is plus 30 degrees. What about this one? Plus 60 degrees, right? So that's how declination works. And of course, if you're good at 1, 2, 3, 4, 5, 6, 7, you can draw a bunch of circles. 1 degrees, 2 degrees, 3 degrees, 4 degrees, and so on and so forth. That's declination. It's north-south of the celestial equator. That's kind of like the y-coordinate, so to speak, on the sphere. Okay, any questions about that? Right ascension is kind of like the x-coordinate. It's like longitude on the Earth. Right ascension is measured along the celestial equator, and any points that are along the same circle, straight perpendicular to the celestial equator, all have the same right ascension. Just like if I go on a line perpendicular to the x-axis, all of those points have the same x-coordinate. So we use this funny system. We could have done it in degrees. We could just make it degrees along the celestial equator, but because the Earth turns once in 24 sidereal hours, we measure the right ascensions in time units to represent that. Because in other words, after 1 sidereal hour, the celestial sphere turns through an angle of 1 hour of right ascension. After 2 sidereal hours, the celestial sphere has turned through 2 hours of right ascension, so it makes it convenient for astronomers to use time units. It wraps around, so we need a point to call 0, and the point we pick is the March equinox. We just pick the March equinox to be 0 hours of right ascension, and then as we progress around, 0 hours, and then 1 hour, 2 hours, 3 hours, and then until you get back to 24 hours, but just like 360 degrees is back to 0 again, 24 hours of right ascension is back to 0 again. And so in this case, if you count carefully, then let me think for a second. This is, so it's 1/4 of the way around. We see, each of these is 2 hours apart because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this happens to be marked off. Each of these circles is another 2 hours of right ascension as we go along. So everything along this red arc here has what right ascension? 0, because it's perpendicular to the point where we define 0. In other words, along the celestial equator at the March equinox, that's the 0 of right ascension. So everything along this semicircle has 0 hours right ascension. Now, everything along this circle right here, this semicircle that I'm tracing out, what's the right ascension?
2 hours.
2 hours. How about here? 4, 6, 8, and so on and so forth, right? So if I have, say, this point right here, what's its declination? 30, right? It's on the 30-degree circle. This is 30 degrees declination. What's its right ascension?
2 hours.
2 hours. So this point is at 2 hours right ascension plus 30 degrees declination, for example.
It
Yes?
doesn't matter the order in which those go, right?
By convention, it's right ascension declination. But but you can tell because we say 2h for 2 hours plus 30 degrees. So indicating degrees and hours makes it clear which one is which, as far as that's concerned. Here's a little trickier. What's the right ascension here? What's this right ascension?
22.
Yeah, 22 hours, right, 22. Yeah, because this is 0, which is 24, they're 2 hours apart, so this is, right, we've got 2, 4, 6, 8, blah, 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 20, 22, and then back to 0 again. Yes?
this is also unrelated, so the ecliptic is the path the sun follows.
Yes.
On the celestial sphere, but the
Uh-huh.
ecliptic plane is what Earth is on, even though it's tilted, and that's why we don't get, like, obviously roasted.
Yeah, so, right, so you're right, the ecliptic is the path that the sun appears to follow over the course of the year.
Okay.
And the reason it appears to follow that particular path is because it's orbiting the sun in a plane, and if you take that plane and extend it out until it intersects the celestial sphere, it would cut the celestial sphere in a circle that we call that ecliptic. That's the ecliptic. And, you know, so why is it called the ecliptic? It's because remember that for an eclipse to happen, the moon has to be at one of the nodes of its orbit, or in other words, the moon has to be in the plane of Earth's orbit. The moon has to be in the plane of Earth's orbit if it's to have a chance at blocking us with its shadow or being blocked by our shadow. So in other words, for an eclipse to happen, the moon on the celestial sphere needs to be on the ecliptic. And that's why it's called the ecliptic, because it's where the moon needs to be if there's going to be an eclipse. Because if the moon is not on the ecliptic, that's when its shadow would pass above or below the Earth.
So the ecliptic is what Earth's rotating on, or the sun?
Careful, the Earth is we say revolve when something is going around something else. So the Earth revolves around the sun in the plane of the ecliptic.
Yeah.
What it looks like to us is that the sun is moving on a circle on the celestial sphere that we call the ecliptic. So you have the plane of the ecliptic, which intersects the celestial sphere in the ecliptic circle. What we see as the ecliptic on the sky is the directions to the sun at various points of the year, and it's a circle on the celestial sphere. Yes?
So if the precession of the nodes is every 18.6 years, how is it that we're going to have two solar eclipses, like one in 2017 and one in 2024?
Yeah, so those are like 6 years apart from one another, you mean?
Yeah.
So notice, suppose there was no regression of the line of nodes. Then the line of nodes would point to the sun twice every year. Okay? And so back in 2017, in August, there was a total eclipse of the sun. If there was no regression of the line of nodes, then and it was the way it was back in 2017, then every year in August there would be a chance of an eclipse of the sun and eclipses of the moon as well. August would be an eclipse season, some weeks in August would be an eclipse season, and then 6 months before or after, so September, October, November, December, January, February. August and February would be the months of the year when you could have eclipses, if there was no regression of the line of nodes. And that would be every year. Every year there could be eclipses in August and February. But because of that regression of the line of nodes, the months when eclipses can happen change from year to year. It's always about 2 months every year that can have eclipses, but which months they are is what changes from year to year due to the regression of the line of nodes, because as Earth is orbiting the sun, the direction of the line of nodes is changing, so the next possible eclipses are a little earlier than 6 months later. So that accumulates over time, so that what months the eclipse is happening drifts through the calendar from year to year to year, is the idea. So for example, back in 2009, January and July were the months that eclipses could happen. But in 2005, it was more like something like April and October, for example. The months drift around the calendar because of the eclipses can happen, drift around the calendar because of regression of the line of nodes. Question?
So then, how do you explain like why the sun moves on the ecliptic?
Why the sun moves on the ecliptic?
Yeah.
So it's an illusion. It's what looks like it's happening. So first I'll do it like this. Okay. So suppose I'm the sun, you're the earth. What's behind my head right now? Literally, like what do you see behind my head?
This slide.
Yeah, the slide, right. So, right, it's the constellation Slidula or whatever, right?
Yes.
Okay, so now you're Earth, you're orbiting me. So you orbit me, and about 3 months from now, you're over there somewhere, okay? Is the slide still behind me?
No.
No, what do you see me in front of now? Over there, right? So now imagine that there's stars painted everywhere around here. So right now, you see me in whatever constellation those stars back there make up. A few months later, you see me in whatever constellation those stars over there make up. So in other words, as Earth goes around the sun, the stars that we see the sun in front of is continuously changing. Or in other words, it looks to us like the sun is moving along the celestial sphere from one constellation to another.
But it's really, we're
But it's
revolving
really
on the
us.
ecliptic plane around the sun.
Yes, we're the ones moving around the sun in the ecliptic plane. That's absolutely right. Yes. And so, so we get whatever I'm trying to say. Let's see. So, yeah, I mean, it sounds like you get it, basically, but still, I just want to show the relevant slide. I should probably just pull it up from up here. So, let's
So on the exam,
Mm-hmm.
are you gonna have us draw stuff, or is it more like fill in?
No, I'm not going to have you draw stuff because there would be too many students who are as good at drawing as I am, and then I would be like, oh God. So, I mean,
But it's like,
I can show you pictures, and you should be able to understand what those pictures are telling you.
okay, so we don't have to like fill in a picture or like.
Right.
shade
Well, I could do like, like the lecture tutorials kind of stuff. I could do things like put a letter where the moon would be and blah, blah, blah. But I won't be like, draw the Earth and the moon orbiting the Earth and draw the sun and blah, blah, blah. In other words, there'll be a figure which maybe you mark up. You might decorate figures just like in the lecture tutorials.
Okay.
So, yes.
So for your determining circumpolar stars, is that just 90 degrees minus the latitude?
Yep, it starts at 90 degrees minus the
Yes.
latitude and then goes all the way up to the closest pole. Yeah, so at 40 degrees latitude, the circumpolar zone goes from 90 minus 40 or 50 up to 90. And the reason for that is because, I mean, it's actually, it's not even something you really need to memorize if you know what's going on. The reason for that is we're in the northern hemisphere. So there's north. Here is the north celestial pole. And the thing you need to remember is the altitude, the angle from the horizon up to the north celestial pole is equal to your what on Earth?
Latitude.
Your latitude. So this angle, if we're at latitude 40 degrees north, then that's a 40-degree angle right there, meaning if I were pointing at north and then I swing up to the north celestial pole, I've swung through 40 degrees now. That's not 40 degrees from where you are, but whatever, okay? So, and now that means, and I'm not going to do a good job of this, but if I did a beautiful circle centered on the north celestial pole, right? Pretend that's a beautiful circle centered on the north celestial pole. Everything within 40 degrees of the north celestial pole is circumpolar. Well, what's the north celestial pole's declination? 90. It's at declination equals 90 degrees. So if you're within 40 degrees of 90 degrees, you're circumpolar. Well, what is within 40 degrees of 90 degrees? 90 minus 40 is 50, is the idea. Yeah. Anything closer to the pole than your latitude is circumpolar. Declination-wise, that means subtract your latitude from 90 degrees. And then anything above that is circumpolar.
We're not going to be responsible for knowing all of the constellations, right?
Oh, no. No, this is not a course about constellations. No. That's just on your own time for fun that, learn the constellations. But yeah, no, this is not like, you know, remember Leo and all that kind of stuff. No. That's one thing. Sometimes people misunderstand that. You know, they think they're signing up for this course and they're going to learn the constellations, and sometimes they're disappointed by that. But no, that's just have fun if you want to learn constellations yourself, and I'm happy to help with that. But it's not something we're testing on in this. No.
Is there any hints that we should maybe look at?
I kind of give them on the study guide. In other words, just go through those things. It's really true. Yeah. Seriously, I mean, I wasn't making that up.
Wait, so when you say, I'm sorry, when you say a whole page of multiple choice, I mean long answer, that sounds a little daunting. Does that mean multiple parts, or just you're gonna give us that much space to explain?
It's more like multiple parts, right? Or, you know, sometimes there's a figure there. Because, you know, some of them are, quite a number of them are based on lecture tutorials. So I might grab a figure from the lecture tutorial and see if you could explain what's going on in that figure, for example. Similar to the lecture tutorial. You know, which way does the star move, and how did you know that? You know, that sort of thing. So I'm not looking for, you know, pages and pages of writing. I'm looking for, because if you really understand it, you can explain it in 1 or 2 sentences.
And then I guess my other question is about the star thing, because we just talked about constellations.
Mm-hmm.
They're moving east to west to us because we're rotating west to east.
Yes.
Right?
Yep. They appear to go from east to west because
Like
we're
the
going the
sun.
other way.
Because we're going straight.
Yep. That's right.
Fantastic.
That's absolutely right.
So now you're welcome. I have questions on that.
You're welcome.
But over the course of one night, you wouldn't be able to see a huge amount of difference, correct? It's like over a month span, you would see it moves.
So, let's see, what do you mean by that? When you say over the course of a night, what?
It's not going to move a significant enough amount that,
So, which would you say?
sorry, a
It's-
constellation.
Careful, no. So, in any given night, for example, you might see Orion rising in the east, and then it climbs across, high in the south, sets in the west. And just like the sun and the moon do. Because as we are turning, the entire sky appears to be turning around us. So think back to the celestial globe here, right? Here, I'll put the sun in the constellation Leo. Here's the sun in Leo. Here's the sphere turning. There's the sun marching along. Well, it's in the stars of Leo. It's in front of the stars of Leo. So Leo and the sun are marching across the sky together. So constellations, stars, they rise and set just like the sun and the moon do.
But the sun's movement from one constellation into another is over.
That
the same.
takes
That's
us-
what we're missing.
That takes like a month, yeah. To get to the next constellation over along the ecliptic, that takes like a month. The sun is always moving along the ecliptic, but in any one day, it only moves a total of 1 degree. So therefore, to a first approximation, you can pretend it's just pasted there, not moving over the course of 1 day, even though it is crawling. It's like an ant that's lollygagging very slowly along the sphere while you're turning it around in the other direction. So wait long enough, and you'll notice that the ant walked pretty far, but over one spin, if it's really crawling slowly, it'll only move a little bit, and that's what the sun is doing. It's only moving a little bit in any given day, even though it is always moving, strictly speaking. So I'm actually kept thinking, oh, I still want to show the figure. Okay, finally back to, here's the figure of the idea, here's the sun orbiting the Earth. Kidding. The Earth orbiting the sun.
Fake news!
Yeah, fake news, totally fake news.
Fake news.
Here's Earth orbiting the sun. And what we see, though, is the sun appears to move along the ecliptic because the direction to the sun keeps changing as we orbit it. Now, that's definitely fake news.
Should I get a bonus question on my test now, hold on, please.
If you know that Earth is
No,
the
because I
fake
just
news
corrected
that-
you, that should be a bonus.
Okay, that should be a bonus question, I see, okay.
And the extra credit is 5%.
5 percentage points, right, 5 percentage points. So in other words, if you got an 80% on the exam straight up, and you got all the points on the extra credit, you get an 85 on the exam. So it's basically half a letter grade, roughly
Yeah.
speaking, yeah. Mhm.
Yeah.
Is that gonna be offered every exam, or is that like?
No, this is a special Valentine's Day special. Or almost Valentine's Day.
Well, I appreciate it.
I appreciate that, because I'm very serious.
Thank you for doing this lecture.
Yeah, thank you.
Mhm.
Very
Can you go over the difference between the sidereal month
And the synodic, yeah, sidereal versus synodic month, yes. So it's pretty similar
619.
to the difference between the solar day and the sidereal day, except now it's about the moon going around the Earth as opposed to Earth spinning on its axis. So, this is again, let me find a picture because it's better to do that. So this is, I think the lecture tutorial we did for that was in chapter 4. And then, where did I go? Sadly, no. Okay, well, I'll just find it again. So, this is it. Let's see. Yes. No. Hang on. This is what I want. Okay. So. Right. So for, like we were talking about earlier, for the difference between the solar day and the sidereal day, it's because Earth is spinning on its axis and going around the sun at the same time, and so we need to spin a little more to get the sun back in the same place. It's very similar for synodic month versus sidereal month. So a sidereal month is the time it takes the moon to actually go once around its orbit, actually go 360 degrees. But at the same time that the moon is orbiting us, we're also orbiting the sun. So in other words, let's say that up top there is a time of new moon, moon in between Earth and sun. By the time the moon is done a 360, it's off in the same direction, but it's not in front of the sun anymore because we've gone around the sun part way. So to get back in front of the sun again, the moon needs to keep moving a little further in its orbit, about 30 degrees this time instead of only 1 degree, because now it's been a whole month instead of only a single day, like for the sidereal versus solar day. So the synodic month is new moon to new moon, and the sidereal month is the actual time it takes the moon to go once around is 360 degrees.
Is it just new moon to new moon, or is
You can make it full moon to full moon, first quarter to first quarter, anything you like. Basically, in general, it's same phase to same phase. But usually we just, well, let's just pick one. Let's say new moon to new moon.
Can you give an example of a question where you'd ask about the location of the sun in the sky?
Are you talking about like in regards to like moon phases?
Latitude.
Oh, I
Yeah.
see. Right. Okay. So now let's see. I guess I would do it in more general terms. Like for example, typically. So if you are, say, where we are here in Delaware, okay, then on what day of the year does the sun get highest in our sky?
Summer solstice.
Yeah, the summer solstice, or if we're careful, the June solstice, right? I am not going to ask you exactly what its altitude is on that day, even though, strictly speaking, you're equipped to know it. The way I had you do it was with a celestial globe. So I just want you to understand the concept that it gets higher in the summer than it does in the winter and the implications of all of that.
And then one of the extra credit questions asked, I think it was like number 6, talking about where the moon was in the sky. You can't determine like how high the moon is in the sky, just rather
Right, so
it's
that's right.
west
So
or south,
right,
right?
with the details, you could, if you have the exact parameters of the moon's orbit and the right ascension and declination of the nodes and blah blah blah, you could determine all that, right? But the answer in practical terms to your question is, from what we know, no. So when I'm saying, or when Dr. Hendricks' sheet says, where's the moon in the sky? It's not asking you what altitude was it above the horizon. It's asking you east, southeast,
Okay.
south, southwest, or west.
Gotcha.
The general direction you would face in order to see it, not how high you would move your head up or down to see it. Yes?
In that same kind of regard, when you're asking for a time, I know you said in class, like rough.
Yeah, so we just keep it simple and we just say, well, go ahead and ask your question. I want to assume when.
Well, like, so if,
Like mid-afternoon or.
yeah, like I
Yeah.
should rather say like afternoon if it would be like 3 p.m.
So,
Or would you rather say 3
if I ask for a specific time, if I want you to give a specific time like that, I need to keep it simple to where it's going to be a 3, a 6, or a 12.
Okay.
That's basically what it comes
So
down
just
to.
think of it in the terms of like it goes by 3 basically.
Yeah, it goes by 3. Now, I could say the time is 7 p.m., where's the moon? I could do that because then you just need to know whether the angle's more than 90, less than 90 to tell whether it's crescent versus gibbous or whatever. But if I say the phase of the moon is something, what time is it? I'll always say, if it's a crescent or a gibbous, I'll say halfway between new and first quarter, or halfway between full and third quarter, or something like that.
Okay, because when
Yeah.
they were talking to me today, she said,
It can be,
so I just was wanting to know what.
right, like what, yeah. If I ask you for a specific time, it'll be a 3, a 6, a 9, or a 12, basically, yeah. Otherwise, I'd have to say something like, and the angle is 33 degrees, or something like that. That would allow you to.
What are your average exam scores for the first exam usually?
I don't remember what the most recent one was, but they typically, my exams here in this class, the average tends to be on my grading scale, kind of at the border between B- and C+ is where people typically end up on average as far as that's concerned.
You don't curve.
I sometimes will do that, but it's kind of built into my grading scale.
Right.
Because my grading scale is pretty generous is what it comes down to, so
Okay.
yeah.
So do you follow that?
Yeah, I pretty much do, because I've been doing this long enough that I know where to put it to make the distribution be what I would get if I curved it anyway and used a more typical scale.
Right, okay.
So, yeah.
Thank you.
Yep.
Thanks.
So I had one song that actually was
Right.
So if I could, is it okay if I was in here tomorrow?
To come here?
Yeah.
Oh, yeah.
I should be.
Yeah.
Thank you.
Thank you.
You're welcome.
Thank you so much.
Yep. See you tomorrow.
Good night.
Yep, get some sleep.